Hi, welcome back to Lattice QCD Education videos. In this video, we're going to be discussing baryon operators in Lattice QCD. There will be some complications due to working on the lattice as opposed to in the continuum, which we'll look at in a little bit of detail, but not too much. And then we'll talk a little bit about some of the issues that we have with baryon operators relative to working with meson operators. So to get started, let's discuss the hypercubic group. That's the symmetry group of a hypercubic lattice. That is something that has links of equal length in each of the orthogonal directions connecting the sites in 4 dimensions. Spacetime has a symmetry that is SO3, 1, the group of special relativity. And if we move that into Euclidean space by moving to imaginary time, as we do in Lattice QCD, then we change that over into the Euclidean O4 rotational symmetry. So there's nothing special about O4, that's just all the ways to rotate something in 4 dimensions. When we move that down onto the lattice, we form this other group, which we call H for the hypercubic symmetry group. Now this symmetry group has 5 irreducible representations if we consider just the meson cases. And they look something like this. For example, you can have a wave function that is spherically symmetric. So here's the equation for a sphere, which we all know, x squared plus y squared plus z squared. If we attempt to rotate this in our hypercubic group, we'll find that it's always the same. No matter what rotation we do, because it's spherically symmetric, we always get back exactly the same thing. We call this irreducible representation A1. It has only one element to it. That's all there is to it. In A2, we have something that's a little bit different. So we still have all 3 dimensions represented equally, but in this case, we're going to multiply them all together. This is sort of like a hyperbolic sheet. But rather than being the same in all dimensions, in all directions that is, it's different depending on whether we go in the positive direction or the negative direction. We get a different sign depending on which way we're going. So when we rotate this thing, we actually see differences depending on which way it's facing. But at the same time, there's only one way to combine all of these dimensions in a unique way. And so we call this group A2. Now we can find that there are more complicated groups. They're still pretty simple. We can take 2 of our dimensions and subtract them from one another, x squared minus y squared minus x squared, and this defines a little group that has 2 elements, which we call E. A third group is just the regular pick a direction, go in it. Which direction do we pick? It could be x, it could be y, it could be z. This is what we call the vector group, T1. Just pick a direction, go in it. And then the sort of conjugate to that would be pick one dimension and don't include it, but include the other 2 dimensions in a way where they are equally treated. So we have here yz, zy. You see x is special because it's been taken out. Zx plus xz, xy plus yx. So this is what we would think of as being sort of an axial vector group. And this one we call T2. Now, no matter what we do, rotational symmetry will be restored when the lattice spacing goes to 0. But for any finite lattice spacing, we need to remember that we're not really working in a continuous space where we have the ordinary angular momentum operators. We're really working in this hypercubic group that rather than having angular momentum, falls into these 5 irreducible representations. So let's talk a little bit about how you would build a baryon operator in the first place. So a baryon, of course, is something that has 3 valence quarks. And the basic 3 quark building blocks are going to look like this. We denote it by B for baryon. It's got a bar on top because it's a creation operator. We label it with capital ABC, which are going to be our quark flavors, ups and downs, that sort of thing. We label it on the bottom with 3 alpha, beta, and gamma. These are going to be Dirac indices. They're going to describe the spin characteristics of this particle. And internal to this operator, there are also color indices, I, J, and K. But because the baryon is, of course, a color-neutral operator, these three indices, I, j, and k, are actually contracted out using this epsilon. These fields are nothing more than the ordinary quark fields of some particular quark flavor, Dirac index, and color, as described here. But when we do this on the lattice, we don't just get a baryon of the angular momentum that we want, we get something that's projected onto the irreducible representations of the hypercubic lattice. And we need to do this carefully, or else we'll get a bunch of spin projections for particles we're not really interested in. We want to project exactly onto the particles that we're interested in the continuum. So let's take a little closer look. Generally, the way we're going to denote these things is by capital B, again for baryon, but now we're going to denote this according to its irrep on the lattice, which we denote by capital lambda here. And there are a whole bunch of these different ones. As we said before, there could be 1 to 3 if you're doing mesons. For baryons, it's a little different. We'll see that in a second. But for however, whatever the dimensionality of capital lambda is, little lambda is going to index over those things. And then n is just going to be an element of the interpolating operator, just something to keep count of different ones. So we have some set of coordinates that are going to be the projection onto the correct irrep. Then we're going to have a whole bunch of different baryon operators. And from these, we can just construct our correlator matrix, as we always do. We have a creation operator at 0. We have an annihilation operator at some other space-time point. And we're going to sum this over all of the elements of the same irrep, because those should all be exactly the same particle. Even when you're on the hypercubic lattice, all the members of the irrep should be the same physics. And we sum that over all space because we're doing a momentum projection here. And this process is described in a little more detail in this paper by Bazak et al., if you're interested in seeing more details. So when we want to find an excited state baryon operator, not just the ground state, of course, you can always just wait, and as long as you have any overlap onto it, at large times, you will come down onto the ground state. But if you're interested in an excited state, you need to be a little more careful. You need to project only onto excited states and not onto the ground state at all. So we're interested in baryons that have all sorts of different spin states. We're interested in spin 1/2, that's the ordinary nucleon. We're interested in spin 3/2, for example, the delta. We're interested in the even more excited states of these things, 5/2, and so on, all the way up. But the rotation symmetry is reduced due to the discretization on our lattice. One of our dimensions is already special. It's time. We're going to do a projection onto momentum that's going to pick out a special direction, the time direction. Of the remaining directions, so now we've moved down from all of space-time to just space, we break the rotation group O3 down to what we call the octahedral group. These are the symmetries of the cube. They're also the symmetries of the octahedron. Why they chose to call it the octahedral group instead of the cubic group, I'm not really sure. That's just a notational issue. What we have here is what's called the character table of the octahedral group. This is a really useful way of determining the properties of this group, and in particular, what its irreducible representations are. What this does is it organizes all of the members of that group into different sets. So for example, the first thing here is I. I is the operator that does nothing. There's only one of it, does nothing. J is the operation that we normally call parity. It flips all of the axes. So 6C4 is the group of all operations where we rotate this cube across an axis that penetrates one of the faces of the cube. The 4 denotes the number of times you have to repeat the operation in order to get back to the identity. In this case, if you take a square and you rotate it 90 degrees, and again, and again, and again, the square goes all the way around back to its original side that was up, and you are back to the identity. And the 6 represents the 6 different ways that you can run this axis through the cube. There are 6 different faces of the cube, so there are 6 different operators in this particular little group. Here's another example. In this case, we are taking an axis that runs through the edges of the cube. There are 12 such edges, so the number in front is 12. But once again, we can rotate this 1, 2, 3, 4 times around and get back to the identity, so the number in the subscript is 4. The rest of these are sort of similar to that, but I won't try to recite them off the top of my head. The number in the subscript denotes how many times you have to go through the operation in order to get back to the identity, and the number in front tells you how many such operators there are. In the rows of this character table, we have the irreducible representations, which you may recognize from the earlier slide. We have A1 again. It's the one that's completely spherically symmetric, so no matter what we do, it responds in exactly the same way. Its character is 1, 1, 1, 1, 1, all the way across. In the vertical column here, we have the dimensionality of our irreducible representation. So you recall there's only one way to make this completely spherically symmetric, so this character is 1. For A2, this is also 1, but you can see that A2, unlike A1, has different responses to these various different sets of operations. And the way that we can solve for this character table involves some complicated mathematics. But one interesting thing to note is that the dot product between any two of these rows is going to be equal to 0. And another interesting thing to note is that the sum of the squares of this column will add up to the total number of operations in this entire group. In fact, that's how you solve for the irreducible representations in the first place. But in addition to the meson irreducible representations that we had before, there's an additional complication due to the fact that we're working with spin 1/2 particles as well. We get what's called a double cover of the octahedral group. You may recall from your quantum mechanics classes that you can rotate a spin 1/2 object all the way around, and rather than getting back what you started with, you get the same wave function but with a minus sign. You have to go all the way around again in order to get back to the original thing that you had. That introduces a few more irreducible representations. There are 2 of them which have 2 dimensions, which are called G1 and G2, and there's a new one that has 4 dimensions called H. These are the baryons. And I won't go through the difficult math here, but you can use this character table in order to determine how the continuous group of O3 and its irreducible representations, which you may recall are these angular momentum ones given by different spins, 1/2, 3/2, 5/2, and so on, are broken down into these octahedral group representations, G1, G2, and H. In the case of J 1/2, it's quite simple, you just get G1, no problem. And in the case of J equals 3/2, we just get H, also very simple. But in the case of J equal to 5/2, we get both G2 and H. So what does this mean? Well, on the lattice, remember that we don't create an operator that's in a representation of J, of the angular momentum in continuous space. We can only create operators that are in irreducible representations of the octahedral group. So suppose we come up with an operator that is in H, and we wish that this were in spin 5/2. We're interested in a spin 5/2 baryon. Well, we can't exactly do that because the irreducible representation H appears in both spin 3/2 and spin 5/2. So our irreducible representation H operator will have overlap with both of those kinds of baryons. Now we can craft it in such a way that as we go to the continuum limit, we expect it to become more and more like the continuous irreducible representation. And those tricks seem to work pretty well. But generally, when you have an operator, it's in an irreducible representation of the octahedral group, and you can get overlaps with other spins. In order to get a clear signal for these operators, generally what we have to do is take very many different kinds of operators. You don't know a priori which operator will have the best overlap with the actual physical particle that you're interested in. So you just take a bunch of different operators that have the quantum numbers of the object you're interested in, but differ in other ways. Maybe they're smeared out to different sizes. Maybe they have different internal spin structures. Maybe they have different spatial structure on the inside, displacements, for example. It could be anything. But when you have all of these together, you can solve this generalized eigensystem equation. And when you get these eigenvalues, lambda of t and t naught, these will have the same properties as the correlators that we studied in the simplest case. And you'll be able to extract not just the ground state energy, but usually several excited states from this as well. Here's an example from a quenched anisotropic lattice. Now, anisotropic is a kind of lattice that is not hypercubic. It has cubic symmetry, but the fourth dimension is much finer than the spatial dimensions. So this particular lattice has an inverse lattice spacing in the time direction of 6 GeV, which is very high. That allows us to extract the excited states with a great deal of precision. We use Clover action, and we have a very heavy pion mass, 680 MeV. In this case, we're using a matrix of 5 by 5 smeared correlator matrices. So that means each of the operators has a different smearing. There are 5 different smearings. We use 5 different sources, 5 different sinks. We get this correlator matrix. We fit each of these individually to an exponential form and show them along with the effective mass. And you can see here, using the variational method, we've managed to extract several different states. The ground state is here in brown, and you can see its signal extends very far across this lattice, all the way up to time step maybe 51. But there's also a state here in orange that we can pretty much extract up to about 15. Likewise with this green state, a blue state above it, and even this black state at the very top. All of these can be extracted just from the simple trick of using the variational method. However, the challenge for baryons is always the noise problem. And why does this noise problem happen, and why is it such a problem for baryons? Well, as we go to lighter pions, we need more and more and more statistics. The reason for this can be seen pretty simply. If we consider our signal of some operator, which we'll call J, to its noise, well, what's the noise of this operator? Well, we just use the formula for variance. It's the difference between the expectation value of the operator squared versus the square of its expectation value, right? That's the definition of variance. And we have a factor of 1 over root n because this improves as a function of how much statistics we have. So if our signal has some exponential form at large time, we go down onto the ground state. And our noise, so if we take a 3-quark operator and we square it, we can get either 2 nucleons, which is what you would get in this case, where we take the signal from this, the nucleon, squared. But if we take this part, where we have 3 quarks and 3 anti-quarks, and we put them together, we can actually rearrange all of those, not into 2 nucleons, a nucleon and anti-nucleon that would be, but into 3 pions. And that'll have a much lighter mass if our pion mass is quite low. And so our signal-to-noise ratio will not be constant like we might wish, but rather will go as e to the minus the difference between the nucleon mass and 3/2 of the pion mass. And that's why we're always in this sticky situation with noise, needing more and more statistics for our baryon correlators. Thanks for listening to this lecture about baryons and their difficulties on the lattice.